Good morning, all. We are in biasing techniques. Today, we are going to discuss another bias circuit configuration, that is collector to base bias, or simply a collector feedback bias circuit. This is also called collector feedback. Here, observe that here this is the collector node. This collector node, it is common to both input and output. Right here, some part of output is again connected to the input. Right, some part of output. Okay, here the collector, here we have to take the output voltage. Here is some part of this output voltage is again feedback and given to the input. Right. Okay, observe here this, so that this is also called collector feedback circuit. Collector feedback circuit. Okay, so far we see the different bias circuits. Okay, one is fixed bias circuit. In fixed bias, this RF or some textbooks RB, base bias, sorry, base resistor, RB or RF. Okay, why it is called RF means feedback resistor. Collector, here the resistor RB or RF is connected between the input node and output node. Okay, here the collector is the output node, so that the feedback, right, output is some portion of the output is again connected to the input, right? So collected to base, some portion of the output again connected to the input through resistor RB. So some portion is again connected to input, that is a feedback. So that's why RF. Or as usual, normally it is connected to the base. That's why base resistor, RF or RB resistor. Okay, in fixed bias, this RB resistor is directly connected to the VCC. Okay, what we seen in first bias circuit, fixed bias circuit, RB directly connected to the VCC. Now, instead of connecting the VCC, this RB is connected to the collector node. Now we have to analyze the circuit. Analyze means we have to find the base current, find the output voltage. Once you know the base current, I can easily calculate and derive the collector current expression. Then we can easily draw the DC load line and also stability factor. Okay, this configuration employs a negative feedback to prevent the thermal runaway and stabilize the operating point. Okay, compared to previous circuit, the stability of the circuit is increases. Why? Because it will provide some negative feedback. Okay, so far we don't know what is the positive feedback and what is the negative feedback. In detail, in amplifier circuits, in detail we study the different types of whether it is a voltage amplifier or it is a current amplifier, whether it is a what type of feedback. Okay, all this comes in their amplifier circuits. Okay, now up to that, here this is the negative feedback circuit. Due to this, it will prevent the thermal runaway, so that the operating point is more stable compared to previous bias circuit. Okay, in this form of biasing, the base resistor RF is connected to the collector instead of connecting to the DC source, right? So any thermal runaway will induce the voltage drop across the resistor RC that will throttle the transistor base current. Okay, we will see how the Q point is stable compared to previous two bias circuits. Okay, for any bias circuit, only the analysis is coming to the analysis is one is input section. This is the input portion. We have to apply KVL to this input loop. And second one is, and by using input loop, we have to derive the expression for IB current, base current. Okay, and the base current is, there are two different types of expressions, base equation. One is in terms of IC, one is in terms of IC, and second one is in terms of resistors and power supplies. Right? We have to derive for any bias circuit, we have to derive the base current expression in terms of IC. That is the first method or first category. Why? Because in terms of IC means then only we can easily find stability factor. What is stability factor? For to find the stability factor, we require DIB by DIC, right? Okay. To calculate the stability factor, we require base current expression in terms of IC, collector current, right? Now to find the stability, to find the Q point, all these things, we require, or we may express IB current in terms of resistors, whatever the resistor here, RC, RB, and some bias voltages like VB and DC sources and DC sources, right? So by applying KVL to this loop, derive the base current expression in terms of collector current, in terms of resistors and junction voltages and DC sources. Okay. Now first one, IB in terms of resistor values, right? Okay, what is the here the circuit diagram? This is the common to both here. Now this is emitter is connected to ground. Now there is a one feedback resistor RF or RB, and that is given here. Now indicate clearly bias voltages VCC, and this is the base, and this is the emitter, and between this base and emitter VBE junction voltage. Why? Because VB is forward bias. Okay, for silicon it is at 0.7 voltage, and this node is collector node, and here this is the output. Okay, now here the current directions are important. Here the current flowing through the transistor through collector terminal is IC, and through base terminal is IB, right? Okay, here the current is IC current, here the current is IB current. What is the current through resistor RC here? Okay, observe here, this is RC and this is RB. Now current through, okay, I will take black, right? Current through resistor RC is equal to sum of IC plus IB. Remember this one. Current through resistor RC is equal to IC plus IB. Okay, IC plus IB. So, okay, here you may check with KCL, Kirchhoff's current law. Incoming current is equal to outgoing current. What is incoming current? Incoming current is IC plus IB. Outgoing current is one path is IB and another path is IC. Okay, now this is the circuit configuration here. Now we have to apply the KVL at input loop. This is the input loop. Remember here. What this loop contains? This loop contains VCC, RC, RB, VBE and ground. Remember this one. This loop contain, this is the path. Here we have to start the path here. This is VCC, then RC, then RB, then base, then VBE and ground. Now we have to apply KVL to this loop. What is the expression? VCC. Okay, here I am considering the second terminal. Either you may consider first terminal also, right? VCC minus what is current flowing through the RC? RC is equal to IC plus IB into RC minus, and current flowing through RB is only IB into RB minus, that is the junction voltage VBE is there. Okay, base to emitter voltage VBE is equal to 0. Now simplify this one. Now again here substitute the condition IC is equal to beta times IB. Okay, why I am replacing IC is equal to beta times IB? We are representing the base current in terms of resistor values and junction voltages. So wherever I see here, this is IC. IC is replaced with beta times IB RC as it is. IB RC, IB RB minus VBE is equal to G. From that here, take common here IB take common beta RC plus RB. Then again in this, take common RC, 1 plus beta plus RB minus VB. Now here IB is equal to base current expression in terms of resistor values and transistor parameters and supply and junction voltages. IB is equal to VCC minus VBE by RC into 1 plus beta, sometimes beta also called HFE, right? RC into 1 plus HFE plus RB. Now ICQ is equal to, once you know the IB base current is fixed, right? Observe here, almost this one is fixed. VCC fixed, VBE fixed, RC fixed. For a given transistor, beta also fixed, RB also fixed. So that IB base current is fixed. Okay, now ICQ is equal to beta times IB or HFE times IB. Right? Okay, already you know the DC load line concept here. Once you know the base current is fixed once, then the load line, we can easily find ICQ. This is ICQ and this is VCQ. Right. Now ICQ is equal to beta times IB, or ICQ is equal to HFA into IB. Now output section, right? Now output section, what output section here? This is the circuit diagram here. Output section consists of, what is the loop here? This a loop. This loop contains one is VCC, RC. What is current flowing through RC? IC plus IB. Remember here. And there is a junction voltage VCE. Okay. At input side, junction voltage VBE at input side. At output side, junction voltage collected to emitter junction. Okay. Now apply KVL to this loop. VCC minus RC. Current flowing through RC is IC plus IB minus VCE. Okay. This is the junction or output voltage. Minus VCE is equal to 0. So VCC minus RC into IC minus RC into IB minus VCE is equal to 0. Okay, compared to IC, already we know that what is the relation between IC and IB. IC is equal to beta times or HFE times IB. So that we may neglect base current here. Okay, so RC into IC is beta times greater than RC into IB. So that you may neglect this term RC into IB term, then the remaining expression is VCC minus IC RC minus VCE is equal to 0. From that we require a VCEQ because we require some DC load line means what is point here? You made this point and this point. This is the ICQ. This is ICQ. Now this is VCEQ. Right. Right. So VCEQ is equal to VCC minus ICQ into RC. Okay, this is the output section, right? Okay, this is the summary of previous two derivations here. So IB in terms of resistor values and junction, all these things, IB is equal to VCC minus VBE by HFE plus 1 into RC plus RB. ICQ is equal to HFE into IB. VCEQ is equal to, then finally approximately VCC minus ICQ into RC. Okay, now here it is the problem here. If the given VCC is equal to 10 volts, RC is equal to 1.5 kilo ohms, RB is equal to 180 kilo ohms, and HFE is equal to 100. Okay, determine ICQ and VCEQ, right? Okay, for that we require a base current. Okay, already we derived the base current expression in terms of resistor values. Why? Because initially we don't know the collector current. So that base current in terms of resistor values and other parameters. So that we IB is equal to 28.05 microamperes. Then ICQ is equal to HFE into IB. Okay, here HFE is equal to 100. 100 is multiplied with 28.05 microamperes. That is equal to 2.805 milliamperes. Okay, now after that VCQ is equal to VCC minus HFE. Okay, HFE plus 1 into IB into RC. Okay, here the question marks all are multiplication here. Okay, all these question marks are multiplication. Right. Now VCEQ is equal to 5.75 volts. Okay. So simply substitute the values here, the previous expressions. Okay. This is the expression here, VCEQ expression. This is the IB, then this is the ICQ, right? Okay. Now, already we know the VCEQ and ICQ. Then how to draw the DC load line here? DC load line is drawn between here the maximum VC is equal to VCC point here. Then maximum collector current approximately here, what is here? VCC by RC. VCC minus VC neglect. Then 10 by 1.5 around 6 milli, approximately 6 milliamperes here. What is expression here? IC max is equal to not ICQ. This is IC max. IC max is equal to approximately equal to VCC by VCC minus VCE by RC. Okay, that is IC maximum. Then VCE max or VCE of is equal to VCC. So VCE max is equal to VCC, right? Okay. Now substitute values here. Approximately this one is 10 volt here. Okay, VCE maximum is equal to VCC 10 volts, and collector current that is equal to 9.7 by 1.5. Okay, anyhow, this value becomes anyhow this value becomes 6 milliamperes. Okay. Okay, here it is the 10 volts. This is VCE maximum is equal to 10 volts, and this is IC. Okay. Now we calculated the ICQ. What is ICQ? 2.8. Okay, nearly approximately maybe like this. 2.8 and VCEQ. So this is VCEQ. What is the value? That value is equal to 5.75. VCEQ is equal to 5.75 volts, and ICQ is equal to 2.8 milliamperes. Okay. Nearly approximately middle of the DC load line. Q point is located approximately middle of the DC load line. Okay. Now we have to express the base current in terms of IC current, right? Why? Because to derive the stability factor expression, we require a base current in terms of collector current. Okay, now consider the same circuit here. What is the circuit? Okay, this is RC, and this one is emitter is connected to ground, and there is a one resistor, and that resistor is connected here. This is collector point, this is VCC, and this is RC. This is RB. You can now apply KVL to this loop, same as previous condition here, and there is a base to emitter voltage. Okay. What is here? VCC minus what is current flowing through this RC, that is equal to IC plus IB. IC plus IB, and current through RB only IB, and current entering to the transistor is IC. Okay, now apply KVL to this loop. VCC minus IC plus RB into RC minus IB RB minus VB is equal to 0. Now here simplify. VCC minus ICRC minus IBRC minus IBRB minus VB is equal to 0. Then VCC minus ICRC, take common IB here, RB plus RC minus VB is equal to 0. Then IB base current in terms of collector current is VCC minus VBE minus ICRC by RB plus RC. So this is the base current in terms of collector current. Now stability factor. Okay. Stability factor. First, derive the stability factor. We require base current in terms of collector current expression. Already we derived the base current in terms of collector current. That is IB is equal to VCC minus VBE minus ICRC by RC plus RB. Then differentiate above base current with respect to collector current. DIB by DIC is equal to, okay, this is constant, this is also constant, constant of differentiation 0. Then remaining term is only this term. What is the term? Term is, this is the term. ICRC by RC plus RB, right? Okay, then DIB by DIC is equal to minus RC by RC plus RB. Then we know that this is the stability factor expression. S is equal to 1 plus beta by 1 minus beta into DIB by DIC. Then substitute here. Then the final expression is S is equal to 1 plus beta by 1 plus beta into RC by RC plus RB. Okay. Now, if you substitute all values, this value is smaller than 1 plus beta. Why? Because in fixed bias, what is in fixed bias? S is equal to 1 plus beta in fixed bias, right? So, now when we substitute all this value, why? Because here observe here denominator 1 plus beta times RC by RC plus RB. Definitely this value is less than 1 plus beta. Or if we require stability, okay, your design criteria is only stability factor. If we choose the resistor value such a way that RC very much greater than RB. Okay, of course, to maintain this condition, we require some other properties like a very high VCC, etc. Okay, if we require the stability factor point of view, okay, if we choose RC very much greater than RB, then you may neglect this RB resistor here. Then RC get cancelled, and again 1 plus beta by 1 plus beta also get cancelled. Now at that case, stability factor approximately equal to 1. Okay. When stability factor value is very small, then the stability of the system is very, very high, right? Okay. The condition here it is this bias circuit, collector to base bias circuit, it will provide the stability factor value is less than 1 plus beta. Or if we choose the resistor value RC very much greater than RB, then stability factor approximately equal to 1. Okay, same here. What we have to previously, stability factor is equal to 1 plus beta by 1 plus beta, RC by RC plus RF. Okay, here it is the problem here. Here the problem is a given network is a collector to base. Here the given network is collector to base here. VCC is equal to 20 volts. RC is equal to 4.7 kilo ohm. RB is equal to 680 kilo ohm, and beta or HFE is equal to 120. Okay, determine ICQ, VCEQ, VB, VC, VE, and VBC. Right? Okay. For this one already we derived the expression here. Base current IB is equal to VCC minus VBE by RB plus actually 1 plus beta times RC, beta very much greater than 1. So beta RC. Okay, observe here. Okay, we go for previous. Not this. Okay. Observe here. What is IB is equal to VCC minus VBE by RB plus here HFE plus 1 into RC. HFE very much greater than 1, so that we may neglect this one here. Then the remaining expression is VCC minus VBE by RB plus HFE into RC. What is the remaining expression here? VCC minus VBE by VCC minus VBE by RB plus HFE or beta times RC. HFE or beta times RC. Okay, this is approximately equal to. Okay, same that expression is used in this problem here. Okay. So IB is equal to VCC minus VBE by RB plus HFE or beta times RC. So now the current base current is equal to 15.51. Now what is collector current at operating point? ICQ is equal to beta times IB 1.86 milliamperes. Then VCEQ is equal to 11.26 volt. Okay, now how to check whether these values are correct or not? Observe here, what is VCC? VCC is 20 volt. What is VCEQ? VCEQ is 11.26. Okay, approximately around this will become, okay, this is at 20 volts. Here VCEQ is located at 11 point something. So that around this is at middle of the DC load line. Okay. Similarly here, what is here? uh, IC maximum. What is IC maximum? VCC by RC. Here the 20 by 4.7. Okay, around we can take 5, 5, 4, the 20. So that maximum value is, this is 4 milliamperes. Okay, here it is the 20. Now what is ICQ? ICQ around 1.86. Right. This is 1.86. So the Q point is located approximately middle of the DC load line. Why? Because here we see Q 11.26 volts here, 11.26 volts. Here ICQ is equal to 1.86 milliamperes. Okay, this is also milli, this is also milli. So Q point approximately, look, not exactly middle of the DC load line, approximately it will be located middle of the DC load line. Now specifically what is the voltage? What is base voltage? Observe here, base voltage with respect to ground, it is nothing but base to emitter voltage, VBE, that is equal to 0.7 volt. Why? Because BJT or transistor act as a amplifier. One of the important criteria is base to emitter junction is forward bias. Remember this one. This condition must satisfy. Base to emitter voltage or this junction is forward bias. VB base voltage or base to emitter voltage is equal to 0.7 volt. Now similarly collector voltage. Similarly collector voltage VC or VC. Why? Because here emitter is connected to ground, directly connected to ground. Emitter terminal is directly connected to ground. That's why VCE is equal to VC, VBE is equal to VB. That is equal to 11.26 volt. Already we calculated VCE. Okay, now emitter voltage VE, here the emitter directly connected to ground, that is equal to 0 volt. Now what is VBC? Okay, base to collector junction. This junction is reverse bias. Okay, VBC is nothing but VB minus VC. VB is equal to 0.7. VC is equal to 11.26. Then around minus 10.56. That means what it indicates here, this base to emitter junction is, this junction is forward bias, but this junction is in reverse bias. That means what it indicates, now the amplifier configuration is active region, forward active region, or simply active region. Okay. Now for the same values, suppose we have to calculate the stability factor. What already we know that for the stability factor, what is the expression here? Go for back. Okay, this is the expression. 1 plus beta by 1 plus beta RC by RC plus RF or RB. Okay, either it is a feedback resistor or base resistor. Substitute the values, whatever the given values here, beta, RC and RF. Then stability factor is equal to 66.34. When you substitute all these values, beta, RC, RB, then the stability factor is equal to 66.34, which is less than beta plus 1. What is in fixed bias? What is here stability factor? Stability factor is 1 plus beta. Okay, here the beta value is equal to 120. 120 means 121 in fixed bias. But here in collector to base bias, stability factor is equal to 66.34 only, right? That means compared to this one is stability factor value reduces, right? Okay. Observe here the circuit stability concept here. As HFE increases, okay, how the stability of the circuit is improved compared to fixed bias means HFE increases, IC increases. As IC increases, VCE decreases. Remember here. What is our VCE is equal to VCC minus ICRC. Okay, what is the expression here? VCE is equal to VCC minus ICRC. Now here IC increases, this IC increases means this VCE decreases. As VCE decreases here, and further IB also decreases here. IB decreases, IC also decrease, but IC does not increase that much compared to fixed bias. Okay, less dependent on HFE and temperature. Okay, so good stability compared to fixed bias and also less dependent on HFE and temperatures. Or otherwise here, what is the current here? Current flowing through resistor is that resistor is equal to IC plus IB here. Okay, IC. As temperature increases here, this current IC increases, obviously base current also decreases here. Okay, apply KCL at this node. IC plus IB is equal to IC plus IB. IC increases here, IB decreases. Okay, IB decreases again, IC also decrease, so that there is a compromise. So IC does not increase that much. Because one way as temperature increase, IC increase. But due to negative feedback, IB decrease. IB decrease means IC also decrease, right? The relation between IC and IB is always this is IC is equal to beta times IB. Okay. Due to temperature, all these things IC increase. IC increase means IB also increase. But due to negative feedback, IB decrease. IB decrease means IC also decrease. So due to this one, IC does not much depend upon temperature and HRQ. Okay, this is the summary of collector feedback characteristics here. The base resistor is connected between the base and collector terminals of transistor. Coming to the advantages, it is a simple circuit, relatively stable Q point. Okay, disadvantage, relatively poor AC characteristics. Applications is used primarily to bias linear amplifiers. And once again, these are the base current equations, ICQ and VCEQ. Okay, and already we discussed advantage here. This circuit stabilizes the operating point against the variations in temperature and HFE. And the drawbacks is, what is the condition? If RC very much large means, then only stability is very high. But here the condition, if RC is large, a high VCC is necessary, which increases the cost as well as precautions necessary while handling, right? And second one is if RF is low. Okay, what happened? Another way is if RF is low means the reverse bias of the collector to base region is small, which limits the range of collector voltage swing. Okay, these are the two drawbacks. If RC increase, for stability point of view require high stability, that means RC very much greater than RF. RC large means VCC large. VCC large means cost also increases. Another one is RF is low. RF is low means reverse bias collector to base region is small, which limits the range of collector voltage swing. And sometimes that may collector swing that leaves the transistor in active mode. Okay. And that is about the demerits. And usage already, the feedback also decreases the input impedance of the amplifier seen from base, which can be advantageous. Due to the gain reduction from feedback, this biasing is used only when the trade-off for stability is warranted. Okay. Okay, this concept we can in more detail while studying the amplifiers. Why? Because okay, here in feedback concept is there, input impedance concept is there. Okay, anyhow, this is used in linear amplifier circuits. Okay, this is about collector to base bias circuit.